Today we'll continue with our discussion of backward chaining, and hopefully by the end of the lecture we'll get into the combination forward and backward chaining a little bit. We'll see. But before that, there's a topic I have to discuss, namely unification, at least at some relatively superficial level. Are there any questions on assignment 5 that I brought out last week? Everybody had a look. Everybody knows who they're working with. Okay, so if you haven't done that yet, you definitely should. Okay, so one of the crucial components of backward chaining was unification, because we were using sort of unknown variables in our clauses in order to communicate results of computation. So if you remember from a lecture from a couple of weeks ago, what we had was something like this. This is from the substructural operational semantics where we have addition. So we're returning some kind of a value m to the stack, and we have a continuation. Actually, let's make this n. That looks like this, right? So the way you evaluate an addition is you evaluate the first part, you get a value and you store it here, then you evaluate the second summand, and that gets a value here. And so at this point you really want to add these two things together, okay? So m plus m as binary numbers. And so now what we'd like to do is something like we compute plus of m and n to give us some result r. And then you return r. Okay. But in order for this to work out properly, we need to make sure that plus can be such that this argument and this argument are given, and the result r can be computed as part of this proof search procedure. And in order for this to work properly, we looked ahead a little bit. So we want return and continuation to be positive. But in order for this to work correctly with our proof search, with our focusing procedure, plus needs to be negative. Okay. So the intuition is that if you have a forward chaining clause and you have something negative on the left-hand side, then we'll compute this as a subproof by doing backward chaining. Okay. Yeah, you have a question? Okay. All right, so that was the thing that we discussed, and then we wrote plus, and we roughly saw how it behaves, but we need to deal with these variables, because by the time we get here, r will be a variable, so we need to be able to handle it. And handling that in general is a process called unification. Okay, so I want to talk about how unification actually works. It's really a little bit separate from linear logic, so I'm not going to spend too much time talking about unification, but just the basic idea. So for the basic idea, I'm going to restrict myself to a small language of terms. Okay, so I'm going to write T. And the language of terms I'm just going to worry about today are either going to be function symbols applied to a sequence of terms, or variables. Okay. And the variables here, these are the ones that are subject to unification. Okay. And what a sequence of terms, well, to make it concrete, we either have an empty sequence or we have some term t followed by another sequence of terms. Okay. So this is just to put some grammar down so we can think about our unification algorithm. Okay. So when we actually call plus in this kind of a situation, we would have like plus would be the first thing here, some kind of function or predicate symbol. These would be closed terms, and r would be a variable when we start because we don't know what r is. So we'll be determining that by unification. Okay, so broadly speaking, the unification problem is this. We have two terms t and s, and we're asking to find a substitution theta such that if you take t and we apply theta to it, that's equal to s. Actually, maybe I shouldn't put this here, even though it's the same thing, so that under the substitution, the two terms become equal. Okay. And what is a substitution? Substitution is something that substitute terms for the variables. Okay. Okay, so for example, to go through some simple example, if we have f of x equals f of c, which in our syntax probably, like officially, there should be some empty parentheses here because I don't have a separate category of constants. But I'm not going to worry about that because you can expand that in your head. Okay. Then the substitution theta that makes these equal is just c substituted for x. Okay. So that's a very simple unification problem. Okay. Let's see. We can make it more complicated. We could say f of x equals f of g of y. Okay. So what is the substitution here that solves this particular problem? Yeah?
Can you just substitute in g for y and y for x, or do you need to?
Okay, so there's one possibility, which is just say g of y for x. So then our substitution here in the terms of a substituting against some free variables. Okay. And so that's a possibility. Now there are other unifiers. For example, we could say, let's say g of the constant c for x. Okay. And c for y, right? That's another possibility. Now these two substitutions are not created equal, even though they make the terms equal. Okay. Any suggestion about what might be different about these two substitutions?
Well, then you can go from one to the other, and the other way.
Right. We can go from here to here by just adding c for y, or substituting c for y in this substitution here. Okay. But we can't go the other way around because we already made the commitment what y is over here. Okay. So when we're actually carrying out unification, we generally want to make the least commitment that we can in order to make the two things equal. So we're generally not looking for an arbitrary substitution, but we're looking for a most general substitution. So that any substitution that makes the two terms equal is an instance of the one that we actually find. And the reason for that is that if you're searching for example, an output here for plus, if you remember, what was the first clause? It was plus of, let's say, n0, m0 is k0 if plus of n and m is k. And our particular goal that we were looking at was try to find some terms so that epsilon 0 and epsilon 0 gives us k. It gives us some result r. And I'm going to write a capital here to indicate that this is a variable. Okay. So if we actually then try to apply this rule, what we want to say, well, r must be equal to k of 0, where k is another variable now. But there's other things that we could do. We could, for example, decide that k should be epsilon 1, 0. Okay. And then r would be epsilon 1, 0. And this term here, so k could be this. And then the two things would be equal. One more. Do I need one more 0 here? Okay. Okay, so that would be another solution. When we try to make this goal equal to the conclusion of this rule, we could say, well, k has to be this, and r has to be this. But then we won't be able to prove that 0, epsilon plus epsilon gives us, let's see, epsilon 1, 0. Okay, and we would have to backtrack and try to make another choice. So generally, when we try to see whether a rule can be applied to prove a particular goal, and I usually indicate the fact that something will go this way, we're trying to do this in a least commitment kind of way. Okay, so the most general way that we can use this rule in order to do this is by saying just all we know is that R should be some k followed by 0, and we don't want to overcommit because we might have to change our minds later. So this is a very important principle, and that's particularly important when you also come to more difficult unification problem like when you try to unify lambda terms, for example. You want to avoid an overcommitment. You want to find a most general solution of the equation that you have and not overcommit, because then you might have to change your mind later, and that's always very expensive. Okay. So what we're trying to find is not just an arbitrary substitution generally, but a most general unifier. Okay. So let's see if we can write down an algorithm to actually do this. Okay. We'll probably need some more examples, but okay. Actually, let's do some examples of things that don't unify. For example, if we have f of x equals g of c, okay, and when I write f and g here, I assume they're two different constants. And of course, there's no substitution that make these two things equal, because no matter what I substitute for x, f is always going to be different from g. Okay. There's another category of things that aren't unifiable. Example, that would be x equals f of x. Okay. So there's no solution to that, because no matter what I substitute for x, the right-hand side always has one more function symbol than the left. Okay. So therefore, these two cannot be equal after any substitution. So this has no solution, and this is no solution. Okay. And there will be more complicated instances of things that don't have solutions, as we will see. Okay. So the way I'm going to write down the algorithm is try to take some of our own medicine and try to write this as a forward chaining algorithm. Yeah, I have a question? So if you had recursive types, you say there should be a solution to this?
Well, they are like isolated. With the fold and unfold with the actual.
Right. So you need more than just recursive types. You kind of also need to allow like infinite terms, right, in order to assign these recursive types to them. Now, there is a unification problem where these two things are not unifiable and these ones are, and that's called unification for rational trees. Okay. And rational trees are pretty much like terms, except they can have loops in them. And so you can point backwards from a leaf back to some earlier point and say the term there is the same one down there. And they stand for the kind of the infinite unfolding. And unification on rational trees is almost the same that we do here, except you don't have such a condition. Okay. And so this is interesting if you want to do, say, logic programming over co-inductively defined terms. Okay. So at some point, Anders, Jacques Nielsen, and Carsten and I think Rob also had his oar in there, where we're thinking about, can you do co-induction? Can you have co-inductively defined terms? But the general case of co-inductive defined terms, even equality is undecidable. So that's a bad start. Okay. Because at least during backward chaining logic programming, well, actually also in forward chaining, equality is like crucial, because when you want to compare your goal with one of your assumptions, you either have to do unification or equality checking. So you need to make some restriction to make this feasible. Okay. And so instead of having arbitrary co-inductively defined terms, you can take rational trees, which is a certain class of co-inductively defined terms. And for those, equality and also unification are decidable. But then we never really pursued it. I guess we really didn't have enough applications, or Anna's graduated, or a combination of the above. Okay. Okay. Okay, other questions? Okay. So now the way I'm going to do this is, may seem a little odd, but it's actually in many ways quite realistic. Okay, so the way I'm going to do this is if I have an equation t equals s that I want to solve, okay, I'm going to assume that, and I'm going to try to derive a contradiction in case they're not unifiable. Okay, so that's my goal. So the idea is that, so if I want to say, okay, so let me just say, we assume t equals s, okay, in our context, and we're trying to derive consequences from that, okay. And if they're non-unifiable, then we want to be able to derive 0, which is a contradiction. Okay. Okay, so what are some of the rules that we might want here? Okay, so this is on the left-hand side of a turnstile, right? Because we're trying to derive some kind of forward-chaining logic program to do unification for us. So the way to think about it is, if we know that t equals s is true, which things are consequences of that? Okay, yeah, you have an idea?
So I guess the form of S and T is four different combinations.
Yeah. Okay. So what's one of the cases?
Variables,
Hmm?
X and Y.
Okay, if you have two variables, how do you... Okay. What do we deduce from that?
Those are substituted with a new variable.
Okay, so that's hard to say because x and y might occur multiple times. So that's not the way we want to approach it. It's a weird way of thinking, but we have done a lot of forward-chaining logic programming. Maybe we can do it. Okay. Yeah?
Do you find that there's some application to that unifies?
Say it again?
Like if you have that,
Yeah?
well, I mean the previous,
Yeah, this one? Okay.
Then that's not the most general form, but then some f of
Okay. Okay, so the problem with this in forward chaining is what?
yeah.
Oh, F and F, sorry. Yeah. Okay, so the problem with this in forward chaining? F is a function symbol, so that's okay. So it's certainly sound to do that, right? If t is equal to s, then f of t equals f of s. That's always the first thing we need to check. So that makes sense. This is good. The problem is that now the rule applies again, right? And again and again and again, right? So we have to think the other way around if we're doing forward chaining. We want to decompose the equation that we have into smaller pieces in order to find a contradiction somewhere. And we hope that if we stop and we haven't found a contradiction, nothing else can be done, that the thing is consistent and represents. Yeah. So we want to do it the other way. I want to say, if we find f of some t's equals f of some s's, let me decompose it into t equals s's. Okay. Okay, so, okay, how would we get a contradiction? Just an example. We may not capture everything, but. So how about this situation? Yeah? Okay, S's, okay. It's the contradiction. Okay.
Also the other case, right?
Okay. This one? Yeah, so this one is harder to do because I could say x equals f of x.
But
That's not really very general. It's just a very special case because it could be that we have, f of g of h of two arguments. First one is a constant, the second one is x. And it would...
be a problem because you can never unify that
Well, okay, we have come back. So this rule is too specific, so we have to come back to this question. Yeah, you have a suggestion?
Yeah.
Oh.
Discretion.
Okay. Okay, so this is true, but it's not very useful in itself.
Okay, but
Yeah.
let's change the, okay, we also want to derive a contradiction. I thought that because the rules that we have do
Yeah.
not allow us to derive a unification.
Right.
Like we cannot derive zero.
We want it to be a decision procedure. Yeah. Right.
So I guess is if x is kind of the same in some f of e and x is in e, so we need a new proposition.
Okay. So if f is some t, x equals f of some t, then we should say x is not in t. Okay, so we need a new preposition in order to get a contradiction if we find x somewhere in here. Okay. How would we write this one?
Another judgment.
Yeah, it is another judgment already. That was the intention, right? This is one judgment, this is one. So we have equality and we have does not occur in.
Recursively, right?
Yeah, recursively. So exactly how does that happen?
Well, if x is in t, like, if x is in something, then, well, sorry, if x is not in t, well, like a list of terms, yeah, then x is not in t,
Okay. What else?
If x is not in x, then there's a contradiction.
Okay.
And if x is not within the f of e, then x is not in e.
Okay.
And if x is not in the ft, then it's fine. I mean, one.
Okay.
Probably constant as well.
Yeah, so constant is just f with the empty list of arguments. So I don't need a special case for that.
So you need when you have a different so x not in y.
Okay. Okay.
X is different from y.
Right. So x different from y. X not in y, we get, what do we get? 1? Okay. I have my doubts about that. Okay. Hmm? Okay, let's go through some more examples here. What about if you say x equals f of y and y equals f of x? Okay. Now I want these to be true at the same time. So how can I encode this as a single problem if I want both of these to be true? Okay, so I have g which takes 2 arguments, and how do I say it? Like this, right? So this has to be non-unifiable, right? But the reason it's not so obvious, right, because x doesn't occur in here and y doesn't occur in there, and still I can't do it. Okay, so how do I continue here?
but in the top, x does occur in y.
Yeah, but it's not one of these equations where I have x is some term. It's some complicated term, right? Okay, so what other things do I need?
Don't we want to be building the substitution as well?
Okay, so in this kind of approach, we don't actually explicitly build a substitution. Okay, so we can go back to the end how we would do that. So in this case, we're just decomposing the term, until we either get a contradiction that we know they're unifiable, or none of the rules applies. And hopefully in that case there is a unifier. Okay, hopefully. But we're not quite there yet. Okay. So this rule seems questionable, right? But so we do need to worry about this case, but okay. What are the things that are true about equality? Yeah? It's transitive, right? We don't have a rule like that. And symmetric. So how about if we say t equals s goes to s equals t? Except, is that how we did symmetry before? Yeah, so this way you can keep changing your mind going back and forth. The way we did it was something like this, right? These were persistent. So, but if these things are persistent, what happens with all the other equations? Yeah, they all need to be persistent. Okay.
Then we can derive contradiction that shows that you might be able to get away with transitive.
Some of them even here.
Yeah, right. So the simplest thing is to say they're all persistent, right? We're just gathering more information about what we have, right? And at the end we could say, well, maybe some of them don't need to be persistent. But it's not obvious if it's going to help if all the things that we generate are themselves persistent, because then even though the premise doesn't require it to be persistent, nothing would really disappear. Okay, so now we want transitivity, right? If t equals s and s equals r, then t equals r. Okay.
And that helps to show that, right?
That should help to
Get rid of this.
okay.
Because if x is equal to y and y is equal to x, then x is equal to f of x.
Right, but these things are not subterms. They're at the top level. So here,
But we should actually have some.
yeah, we don't want to actually substitute into a term, yeah? We want to get the effect of substitution without doing the substitution, right? Because we are tracking what variables can be equal to, right? Variables can be equal to, can be deduced to be equal to other things. Okay, well, let's go through this example. Let's see what this one here. And let's see what happens with the rules that we have so far. So this is a case where we just do persistent logic programming, so things don't go away. Okay. So what rule would we first use here? Well, we would decompose it into the arguments. Oops, we forgot some rules, right? What rules did we forget?
I go from the inequality of lists to...
Right. From an equality of lists to the components. Okay, so what would those rules be? Well, there's 4 cases, right? Let's see, where's a good place? Okay, let's put them down here. So if we have t followed by t's equals s followed by some s's goes to t equals s and t's equals s's, and those should all be persistent, right? So if 2 sequences are equal, then the components must be equal. If we have empty equals empty, then we can go away. Actually, this rule is really redundant in some sense. If these things are persistent, this doesn't really remove it. This rule doesn't do much. But we need 2 more rules. or at least one more rule.
No, we generate a contradiction at the lesser harmful.
Right. So if you have something like mt equals t followed by t's, then we generate a contradiction. Okay. And then the symmetric version of this as well, if we want. If we have t followed by some more, and we ask if it's equal to the empty sequence, we return false. Okay. Now, if our language were typed, then we would probably show that none of these rules could ever apply. Because if at the top level we always start with a well-typed term, then a given function symbol takes only a certain fixed number of arguments, and we would never get into a situation where this one would apply. Okay. But if you don't worry about this, then it's good to have those rules. Okay, good. So we have this as one of our equations. By applying the decomposition rule, we would say x and y equals f of y, f of x. Okay. So now we should be able to apply a decomposition rule, and we find x equals f of y, and we also find y equals f of x. Okay, we can always get the symmetric versions of these. I won't write them down because they don't really do much. What else do we get here?
Well, now we can find the non-native rules.
Okay, so we'd say x is not in f of y, and here we would say y is not, whoops, not in y, right? And here we find y is not in x, right? Okay.
You just have a rule that you have, I guess you might have multiple chains. I would say if you have both x is not in y and y is not in x, that could go to a contradiction, but you could generalize that to have, larger chains of these things.
Yeah. Right, x could not be in y, y not in z.
Yeah.
How do you find that, that there's a cycle of x not in z? Yeah?
So I would suggest adding a new rule saying that if x is not in some term t, and t is equal to s, then x is not in s.
Okay. So if we have x is not in t, and t is equal to s, then x must not be in s. Okay. Okay, let's check.
Actually, I'm thinking of a safer variant which t is a variable, and this can have not.
Okay. Do you want to save a variant, but t is a variable?
That seems
How
safer.
about if x is not in y and y is not in z, then x is not in z.
Okay, x is not in y, and y is not in z, then,
X is not in z.
okay,
That gets rid of that case.
uh-huh.
Isn't it?
I'm waiting for comments on this.
Or doesn't that get rid of that case?
On this particular case, it does, because you would then conclude x is not in x, and that would give you a contradiction by something which we had earlier somewhere. There, yeah. Okay. So the question is: do we only need this, or do we need this, or do we need something with just like a variable here? Okay. Now, it seems like they're all sound, right? Certainly. So the question is if this very restricted form of all of this would be complete or not. Okay. Or if something like this would be needed. Okay. So let's check something. Okay. There's one suspicion I have. If you have x equals y and you have x equals f of y. Okay, let's check this. That should not work, right? Can we capture this? Yeah, we can, because by symmetry and transitivity, gets y is not in f of y. So we would capture that. Okay. So, okay, I hadn't thought of this, but it seems like the last rule there might be sufficient. I'm not sure. Yeah. Certainly the one above should be sufficient, right? It's more general. But I'm not sure if you need it in that full generality. Okay, yeah?
Like since you're decomposing everything already, the last rule is sufficient since all the other rules should decompose them all down.
Yeah. So I think there's a good chance that we should be able to just use the last rule, but I'm not 100% sure. The way to test is to try to prove it, right?
I'm neither, but I just
Yeah. Okay. All right. So we should think about the proof, right? Because in the end, that's what it comes down to. But the nice thing, well, so this is actually quite realistic in some ways, because what you do is if you one way to think about unification problem is that as you go through your search, you add new constraints. Incrementally, as you keep going, you add more and more constraints. And so what you do is every time you get a new constraint, you already have a saturated list of equations that you maintain. If you get a new constraint, you add it, and you run all these rules until you're again saturated. If you haven't found a contradiction, your total set of constraints is still satisfiable. Okay? So the nice thing about this kind of forward chaining algorithm is it's very incremental. Okay? You just keep adding constraints, you saturate until you either find a contradiction, in case then the last thing that you added was the one at fault, or if you don't find a contradiction, then unless you made a mistake, your equation should still have a solution and you can continue, right? So in some sense, you avoid ever really having to compute a substitution, because all you need to know is that my current goal is still possible because the equations are still consistent, and then you continue that way. The nice thing about this is that if you come to theories, if you do not unification just with pure terms, but you have like high order unification, or you're doing over arithmetic constraints, this kind of paradigm continues to work very well even if most general unifiers don't exist. So what you do is you have a set of arithmetic constraints, you get a new constraint, you add it, you normalize in some way enough to check that you still have a solution. If you do, then you continue in the next step and so on. Okay. So this kind of algorithm actually generalizes much more readily to more complicated situations than the one where you explicitly calculate a substitution. Okay. But you must be able to take the things that you know and derive other things from them, and at the end it must be consistent if there's a solution. And if there's no solution, it must return you 0. Okay, so that's the kind of requirement that we have for these things. And modern SMT solvers satisfy modulo theories. If you have, they work essentially in this way. What you do is you get an equation that you know should be true, and you assert it into your database, and you continue to do that. Okay, and the database will do some work behind the scenes, essentially doing forward chaining. And at some point, it might tell you, oh, now your constraints have become inconsistent. Okay, there's no longer any solution. And if it doesn't say that, then you assume that it's consistent because it's a decision procedure, and you can continue with the algorithm. And you don't really have to drill it open. All you need to know is as long as I continue, everything is still going to be consistent. Okay. Okay, but we should think about a little bit at least about how to prove that this all works. Okay. Okay. So we decompose this into a couple of properties. So the one property that we want, that if we have a solution to t equals s, then after we do a forward chaining step, we have exactly the same set of solutions. Okay. And so in order to do that, we need to say what it means to define a solution to a whole set of equations. Okay. But that's not so difficult to see because you just have to solve all the equations, right, simultaneously. Okay. Okay. So how come the solutions are preserved? The theorem that if you have one of these equational contexts and it goes to another equational context by one of these forward chaining steps, okay, and then 1 if gamma of theta is true, if and only, well, actually I can say it like this, gamma theta if and only if gamma prime under theta, okay, is satisfiable, and usually that's written this way because we're talking about this particular syntactic domain, but in general it's going to be some domain whose satisfiability we understand. So we want to preserve the solution space here, exactly. Okay, so we can look, so for example, from here to here, do we preserve the space of solutions? The answer is yes, because there is no solution over here. Okay, there's no substitution that would make these two sides equal, and therefore there's no substitution. And there's no substitution would make this true, and so therefore we preserve the space of solutions exactly. How about here? Okay, so any substitution that make both sides equal, because substitution commutes inside the function symbol, will also make t and s equal, and so therefore this is a consequence. In this direction, if something makes these two things equal, then it also makes this equation equal. Okay. Here, the same thing. Let's see. So this is tricky. Here it's true because equality on terms is symmetric. So this is okay. Transitivity certainly is okay. So it's very easy to see that all the rules preserve the center solution except potentially this one. Okay. So now we need to think about this one here. How would we reason about this? Any ideas? Okay, well, our task would be somewhat easier, maybe if we didn't have to consider this rule. So let's just hope we can do it like this, so we don't have to refer back to this. So what could we say about the not element relationship that might help us in order to prove that the set of substitutions is equal there? Okay, let's try it from left to right. Okay, so we want to say that if we have a solution here, what do we want to say about the right-hand side?
the substitution t for x is so.
Is what? Okay, so I'm trying to prove that the set of solutions is always preserved under these, under going from here to here. Okay, so if we didn't have this rule, okay, for all the other rules, it's pretty easy to see that the set of solutions is preserved, right? So the question is, for this rule, okay, why is it the case that the set of solutions is preserved if we add this rule? Okay.
This is sufficient to argue that all valid solution will lead to contradiction.
Say that again?
All valid substitutions won't lead to contradiction.
Okay, all valid substitution won't lead to a contradiction. Okay. And how do we use that here?
So I'm not sure if we have a definition of the validity of substitution.
Yeah. So
What exactly, if we add this x is not in
yeah.
t bar, then this, how should the set of solutions change? Or
Okay. So if we ignore this rule, right, then it's very clear that all the other rules have the property that if there is a substitution that satisfies such that gamma or theta is true, then this is the case here also. So, but we need this rule for something, right?
But then gamma satisfies, so substitution satisfies x is not in t bar if x is actually not in t bar after substitution or not.
Okay.
What does that mean?
Okay, that's exactly the right question to ask. So what does it mean if we have x not in t and we apply theta to that? When is that satisfied?
To talk about liquid terms, not in other terms, such as the variable.
Okay, do we need to talk about that, or can we just calculate out what that means? So what would that mean? It would mean that if that has some kind of s for x, is in our substitution theta, and this would be s, not in t under theta, right? When would that be satisfied?
Well, what we kind of meant by the judgment is that s and t are different variables, right?
Well, what we meant is that x does not appear anywhere in t, right?
Yeah, but without regard to substitutions,
Right.
right? So when defining the meaning, do we have to actually consider the substitution? Does the theta actually play any role there?
Seems like it could invalidate it. What you are substituting y for x, and y appears somewhere else. And like a term, you have a term x,
Mm-hmm.
f of x comma y. And you want to say x is not in
Okay, so
It has to be true before and after the division.
right. So I'm not sure if this is the right way to think about this, because when you apply a substitution, the contents of this theorem somehow, this judgment somehow goes away, right? Because we want to ask something about variables, and it doesn't really. This is not something that we want to check whether S is a subterm of T. That would be a weird thing. Okay. Okay. So let's push this on the stack for the moment. But let's see what else we want to prove. So one thing we'd want to prove is that this thing eventually terminates, right? Because we want it to be a decision procedure. Okay, so theorem gamma equals always saturates. Okay, or arrives at a contradiction. Okay, how can we prove that this system of forward chaining rules will always saturate? So this goes back to when we started at the very beginning and our first rule was going in the wrong direction. We could get into an infinite loop. So how come we can't get into an infinite loop here?
Create new terms or new variables.
That's right, we don't create new terms or new variables. Okay. So any equations that we deduce are always between terms that we already start with. Okay. So here, while t and s are known, we get s and t. Okay, t and s, we already started with s and r. The new equations between t and r, these are terms in the original term. Okay. So any kind of equation that's generated by these rules, forgetting about the not in, okay, is going to be a subterm of my original term. Okay. So how many subterms are there for a term that I start with? Finitely many, yeah. Sort of order n kind of subterms, okay? If I start with a term of length n, okay? And so how many equalities can I generate, roughly? If I start with a term of order n? Order n squared, right? N possibilities for the left-hand side, n possibility for the right-hand side. Okay. So actually there's a theorem by McAllister and Gunsinger which says that you can analyze the structure of these rules and actually get a very good computational complexity bound on this particular algorithm. In this case it would be order of n squared, okay? And the complexity bound depends on the shape of the rules because you need to fire them, but it also depends on the size of the maximal size of the completed database. And the maximal size of the completed database, if you ignore this for the moment, is going to be order n squared. Okay, so this is like an n squared type algorithm. The original algorithm for unification that Robinson described was exponential. So this is already some improvement over that. One can do better, but that would be the straightforward thing. Now we need to think about this thing here. So how many possibilities for this judgment are there? Right. So it's certainly bounded by order n squared. Or you could be slightly more precise. You could say the number of variables on the left and the number of subterms on the right. So the number of variables times n. Okay. And the number of variables could be order of n. So it's also bounded by that. So eventually this has to saturate simply because the number of possible equations we could derive is finite in this way. Okay. Okay. So it terminates. Okay. So that's good because we want it to be a decision procedure. Okay. And order n squared doesn't actually seem very bad. Okay. Okay. So an actual implementation of this was, I think, of this algorithm more or less, pretty much precisely this algorithm was proposed by Gerard Youet, okay, in, I don't know the exact year. I think it was around maybe 85 or maybe even a little earlier than that. Okay. And he imposed a little strategy on top of this. And the strategy is that you run all the rules that don't have to do with is element in first, okay, to saturation. and you don't touch these rules at all. Okay, you just leave them. And then once you have done those three other rules to saturation, then you run these rules to saturation and see if you can get a contradiction. So you do compare it into you decompose in two phases. One is to what are all the consequences of equality, and the second part is this part here, which is called the occurs check. You try to see if you have created some kind of a cycle. If you try to check for a cycle all the time as you go along eagerly, it could be more expensive. And so in his description of the algorithm, you just do saturation of this, and when you're all done, then you saturate in the resulting equations with these rules. Okay, and you can do better than order n squared because you can kind of maintain equivalence classes of equality by using a union-find data structure, and then you get something like almost linear time behavior for the unification algorithm. Okay. So this is essentially UH's algorithm. There were some similar algorithms. You can do a little bit better than this even if you can order your equalities and the way that you apply these rules in even an even better way, and you can make it linear, which is a result that was obtained by Mortelli and Montanari. And there was another algorithm that is a lot less abstract than this, which was proposed by Patterson and Wakeman just a little bit before proving that it was linear. Okay. But this implementation here, if you don't do any analysis, would be order n squared. With a little bit more work, you can get it order like n log n, or n inverse Ackermann of n. Okay. So it saturates. Okay. It preserves the solutions. And then I guess at the end, one should do something like if it saturates, okay, we should be able to read off a substitution. And that is a little tricky part, because for that, you really need this kind of not in relationship, okay, in order to be able to read off the substitution. So I don't want to spend too much time on that. But what happens is that if you have something like, let's see, x equals f of y, and y equals g of c, let's say, or c of z, okay, then essentially these kind of equations are saturated at this point. I mean, you can add symmetric versions, but you can't really do much more with these. Because here you're supposed to check that x is not in y, which is okay, and this is y is not in z. And so by our rule over there, you'd also get x is not in z. But at that point, you would be kind of done. There's not much more you can do in this kind of thing. And now you'd like to read off a unifying substitution. And it's very tempting to say, well, if x equals f of y, then the substitution theta would say f of y for x and g of z for y. But that actually doesn't really work, okay? And the problem is that you kind of have to substitute this y for this one over here first before you substitute it to make these two things equal, right? Because if you apply substitution to x on the left-hand side and this substitution to the right-hand side, the two things are actually not equal. The left-hand side, it becomes f of y, and the right-hand side becomes f of g of z, right? So this thing is not a unifying substitution, okay? So what you have to do is you have to use the fact that this relationship between variables is acyclic, okay? And you have to define a sequence of substitutions, okay? Okay, and so you start at the variable which is not on the left-hand side of anything, which is z, okay? So theta 0 is just, in this case, like z for z. You don't do anything with z. And then theta 1, you look at the relationship, you say, y is on the right-hand side and the left-hand side here. I already have defined it for z, so now I can define it for y, okay? And then theta 1 is z for z, and theta of 0 for z and g of c. So G of Z under theta 0. And then theta 2 is Z for Z. Hmm? For Y, okay. And then this stays, that part stays the same. We don't have to change our mind on that. And then for this variable x, we substitute f of y under theta 1 for x. Okay, so we have to build up the substitution incrementally. In order to be able to do that, we have to know that there's some kind of well-founded ordering between the variables. Okay, and so then you can prove that if there's a well-founded ordering, which is given by this not-in relationship, then we can build it up incrementally. And then when you get to here, by the time you get here, x, the right-hand side, the substitution does not depend on x. So when we actually apply theta 2 to the right-hand side and the left-hand side, we will end up with the same term, because we cannot get into this kind of situation here. Okay. So the role in this kind of proof of the not-in relationship is essentially in order to allow you to build this unifying substitution along the well-founded order. Okay. Okay, so I think that it actually doesn't play any role in what we wrote down above there in the preservation of substitutions, that in order to prove that, you don't need to talk about the not-in relationship. Okay. Because already, if there's a cycle, this doesn't have a solution, and this doesn't give you any more contradictory power. Okay. Except that you wouldn't be able to find it without that rule, which means you wouldn't be able to find a unifying substitution once you reach saturation. So it doesn't play a role in preserving the set of substitution. It only plays a role in the following theorem: if gamma with equality is saturated and not zero and not contradictory, then there is a Seder such that gamma equals under theta is equal. Okay. And then, since you have preserved the solutions from the beginning of time, we know that theta is also unifier for the original set. Okay. So we don't actually use that in that part of the proof. We only use in this part. Okay. All right. So that's really as much as I wanted to say about unification. Okay. But there's suitable generalizations for other interesting domains using the same kind of technique. And in fact, there's a whole line of research that's called CHR. I should put a reference to that. CHR, which stands for Constraint Handling Rules. Which is a forward-chaining logic programming language in which you can specify constraint solvers just like this unifier. Okay. And not everything has to be persistent. So in this language, you also have some linearity available to you. Okay. And one could imagine that not everything here has to be totally persistent, even though it doesn't hurt. Okay. But there are some other constraint domains for which it's useful to be able to delete equations once you have kind of taken care of everything you know. So for example, it seems like if f of t equals f of s and we decompose it into t equals s, we really don't need that original equation anymore. All the information out of this kind of equality has been squeezed out if you have said that t equals s. Okay. So that would be one place, for example, where we might be able to optimize this kind of algorithm. Okay, so now I wanted to go and talk about at least the beginning of combining forward chaining and backward chaining. Okay, and I will do more of that next time. So what I want to talk about is how to actually make these things interact. Okay, so in this, we already had some programs that we wanted these two things to interact. Okay, so the program that we had was this forward chaining program for evaluation, where we're calling upon some backward chaining goal. So this was something like, so if you have a return, and a cont, and a plus, then we go to another return. Okay, and this was positive, this was positive, this was positive, and the plus was negative. Okay, so we had in mind somehow that as we solve the plus, okay, nothing else happens in the forward chaining. That we basically solve the plus as a completely separate subgoal. Okay, and when this returns, then we add this thing here to our state, and we're over and done with the plus. Okay. Now, in general, this is actually very difficult to achieve in the formalism that we have so far. And the reason is that this decomposes, right? And there's going to be plus as a subgoal here with some arguments. And then over here we have return fuse cont in our context. And we're still trying to prove some goal. So if we're trying to prove some goal, if we're focused on this, while we're trying to prove some overall C, okay, then what happens is, oh, no, sorry, like this. So we have in the context a return and a cont, and now we also have in the context this. So actually it needs to be to the right. I'm sorry, it needs to be on the other side, but this return matches this cont matches this. And this plus will be a subgoal that's solved sort of independently over here. And then we continue by adding the return back into here, and then we continue up there. Okay, so that's the image, what you want to happen. Okay, so the problem now is that we have something negative here. At this point, we have actually lost focus. Okay, because when you have something negative on the right-hand side, you will lose focus. And when you decompose it until you get to the atom, and then you stop. So there's nothing prevent you at all from doing forward chaining over here in this goal. Okay. But that's not really what you want, because you want this to be a subcomputation that has nothing to do with the main forward chaining computation that we're performing. So you want the forward chaining computation to essentially be along sort of the right-hand side of all of these, and there'd be some subcomputation sitting over to the left. But the logic does not actually enforce that. Okay. And so this is sort of the operational reason. There were other logical reasons that we had. But when we designed CLF originally, that's almost like 10 years ago now, okay, we were very conscious that you want this kind of a structure. You have some forward chaining where some subgoals are being solved as backward chaining subgoals as independent computation. Okay, so we wanted to achieve that, force that kind of a structure, okay, based on logical principles. Okay. And so in order to do that, what we wanted to do is to make sure that the forward chaining rules that we have are too weak in order to be able to apply over here. So here we want no forward chaining. Okay. So in particular, forward chaining should be such that it can be used in this context here, but it can't be used over here, and there should be a good logical reason for this to be the case. Okay. All right. So the way we did that is using something else I'd been thinking about at the time, which we called lax truth. Okay, comes from from a different domain actually, and in functional programming, you might be familiar with the concept of a monad, okay, which is the way that this actually turned out. The logical contents of this distinction between this kind of a main branch and these subcomputations is the same idea that this computation here on the right happens in the monad, and the computation on the left is the kind of the pure computation that it doesn't have an effect. Okay, so that is kind of the vague analogy. So now we need to actually write down the rules to make this true. Okay, so today I'll start only with logical rules, and the next time we go into the operation and meaning of them. But at the level of propositions, what do we have? We have like A1, A2, a whole bunch of them. And the new one is going to be this, okay? So where this is like a true in a lax way. And the idea is that if you have forward chaining rules, they will look like this. If A is true, then B is true or in the lax way. And we'll enforce that from B, we cannot prove B. But on the other hand, we can prove from B, we can prove B in the lax way. Okay, so that the lax truth is weaker than the ordinary truth. So it's true under some constraint. Okay, and that means that if you have a forward chaining rule, and we're trying to prove plus true over here, okay, then we can't use the forward chaining rules because the lax truth is weaker than this. And over here we say C is true only in the lax sense. And this judgment does not change as we keep going up with our forward chaining steps. And so the rules for forward chaining can be applied here, okay, because they all look like this. So these are the forward chaining rules. Okay, so now we just need to make sure that we can properly explain the meaning of this by using our standard mechanism of judgments and propositions. Okay, so that's the basic idea. I'll do a lot more detail next time, but let me just give you the idea. So if you have a gamma and a delta, and we're trying to prove lax A is true, then we have to prove A lax, okay, which is a slightly weaker requirement. And unlocking that is the thing that will allow us to use our forward chaining rules here. So now we have a weaker requirement than proving that A is true. Okay, and then we have a judgmental rule that says if we're trying to prove A is lax, one possibility, but that's a real commitment, is proving it true. Okay. So roughly what happens here is that when you do this, you go into forward chaining mode. At some point after however many, arbitrarily many forward chaining steps, you can decide now I'm done, I've saturated or have reached quiescence, and now I actually want to prove the right-hand side. And then you transition back to this. Okay. And what does this mean for the things which happen on the left-hand side? Okay, so on the left-hand side, if I have in delta, and I know this is a resource, and I'm trying to prove C is lax, okay? So then because I'm trying to prove something lax, then I can actually use the assumption that A is true. Okay, because I'm not trying to prove that something is true for which this would be too weak, but I'm just trying to prove that C is lax, and then this is good enough to make the transition to the assumption that C is true. Okay. Okay. And I have some cut rules that go along with that. Anybody care when I hypothesize a new cut rule? We can ignore the gamma because it's really irrelevant for the purpose of this discussion. Okay, so it's pretty safe to go this far. Okay, now we can even put some formulas here. Okay, so that's the usual cut rule. And the usual cut rule, this is true, this is true, this and this is all true. These are all things that are true. Okay, so now we have to change something.
Make A lax.
Right, you want, what can you do with knowing that A is lax? Yeah.
You have to have C lax.
Okay, you need to have C lax. Okay? But it's okay to assume that A is true because you're just trying to prove that C is lax. So you can prove A true or C lax. Okay. So this is a new cut. I guess if you do it in analogy with the bang rule, you write it like this. Cut bang, it would be this. Okay, it's the cut that's concerned with A being lax. Okay, and of course we'd want to show that this is admissible. Okay, we don't really need that rule. Okay. Now we have to make another modification, and this is the more painful part. Okay. We can have a new kind of conclusion that C is lax, and essentially in all the rules that we already have, for all the left rules, okay, you have to allow the conclusion C lax in addition to the conclusion C true, okay, that we had so far. Because the left rule says if we know this, we know that. It doesn't really matter what you're trying to establish. Okay. So the right-hand side is more general than it has been so far. Okay. Okay, so there's some kind of a symmetry here. Okay. Let's see if I can bring this out. First we had truth. Okay, so we had delta true and the right-hand side was true. The things were resources. This was a goal. Everything was simple. And then we introduced bang. We introduced validity. So we had some additional assumption here. These were the assumptions B is valid on the left-hand side. And we put these into gamma and we collected them together. And then we have a transition from B is valid going to B is true. So now, and validity is stronger than truth, right? If it's valid, then it's true. But moreover, you can duplicate it and so on, which you can't do with the linear assumptions. Now on the right-hand side, it turns out to be different. We have a new judgment that's weaker than truth. And rather than collecting multiple ones, we have to make a decision. The right-hand side is either going to be truth, okay, which we had before, or it's going to be lax truth, which is a new thing. So on the right-hand side, you have to make a choice. On the left-hand side, with the validity, we accumulate validity and truth assumptions. On the right-hand side, it's either going to be C is lax or C is true, one or the other. Okay. And then the transition, which copies from validity to it being in here, okay, this is the dual to that. Okay. So the dual to that is instead of proving lax, we can decide that we want to prove truth instead. Okay. So that corresponds to the copy rule, but it's on the right-hand side. Okay. And then the cut rule turns out this way. If you can prove A lax, then we're allowed to assume that A is true, as long as we're trying to establish only that C is lax. Okay. And you can work through the cut proof, and you'll see that this is the cut principle that you need if you're cutting this thing with this. Right? If the right rule is cut against the left rule, okay, then you have to cut this premise against this here. In order to do that, you need that cut principle. Okay. And how would you eliminate this cut? So remember the way you eliminate cut, you push up the cut, right? So how would you push up this cut? Okay, can you push it up into here? Well, if possibly, but there's problems because if, for example, the last rule was that we actually prove C true, then we can't push it up over here, right? Because the conclusion needs to be C lax for this cut principle to apply. Or A might be introduced because it might be A1 tensor A2, then we can't push it up here. Can we push it up here? Well, the conclusion doesn't change. The only way you can ever prove A lax is how? Eventually, the only way is by using this rule. And so you just push it up on this side, okay, and reintroduce all the rules that were used here, okay? And you can always do that because the only place where this A lax could ever be used would be this rule. And so if you hit this rule, then what do? You use a normal cut, right? And just like the other rules, the normal cut also has to allow the conclusion C is lax. It could be C is true or C is lax. Both of those are allowed. Okay. So you eliminate the cut here by pushing it up here until you find this rule, and then it turns into a normal cut. Okay. So for the copy rule, it was kind of the opposite. When we had a cut bang, then we were pushing up into this place here on the right-hand side until it was used, in which case it split into two cuts. One cut was pushing it up into the validity even more, and the other one was with the copy, an ordinary cut on the copy that we introduced. And so here we don't actually introduce a copy, but just make a judgmental transition from here to here. Okay. So this is very similar. So it's almost the case that you have some duality like this. Okay, so that you have bang A somehow corresponds to y naught A, and that seems to be almost the same as A lax. But it turns out, and I'll talk about this next time, that these things are not exactly equal. Okay, so this actually is not exactly the sort of the dual of bang on the right, but very close. So you'll see where that comes in next time. Okay. All right, and then we'll put focusing on this, and then we have a system that combines forward and backward chaining. And so then we can avoid this problem that forward chaining rules are essentially always applicable, because forward chaining rule will only be applicable if we're trying to prove the judgment C lax. And C lax essentially constitutes a monad. So what we're basically saying, as long as they're in the monad, you can do forward chaining. Outside, you just do backward chaining. That's how the division of labor is going to be. Okay, and let me know if you have questions about the homework when you get around to it.